The first section of this tape deals with the internal operation of an oscilloscope. You must complete the first section of the workbook before viewing this tape. Tandy Computer service technicians perform a complex and important job, keeping business and home microcomputers in proper working order. There are many tools available to aid in this exacting task. In this tape, we will discuss two essential computer service tools, test equipment and diagnostic programs. Test equipment is essential for pinpointing failures, performing alignments, and checking specifications. Diagnostics help detect problems and exercise system functions. After viewing this tape and completing the accompanying workbook, you will be able to effectively operate multimeters, frequency counters, and oscilloscopes. You will also understand the basic internal operation of an oscilloscope. You will learn how to use high voltage probes, variacs, and isolation transformers. Finally, you will learn how, when, and why to use various diagnostic programs and how to interpret the results. The first tool that we will cover is our most widely used piece of test equipment, the oscilloscope. Unlike most test instruments, which measure only voltage or frequency, the oscilloscope can provide comprehensive information about a signal. The oscilloscope represents a signal on an electronic graph. The vertical axis represents voltage, and the horizontal axis time. The display area of the scope, called the graticule, is separated into a number of small boxes called divisions. Each vertical division represents one voltage unit, and each horizontal division equals one time unit. We use controls on the oscilloscope to set the value of the voltage and time units. The volts per division control sets the value of each vertical square. In this case, it is set for 1 volt. To determine the amplitude of a signal, multiply the number of vertical divisions covered by the volts per division setting. Since the voltage range is set for 1 volt per division and the signal occupies 5 divisions, this signal's amplitude is 5 volts. The sweep or time-based setting selects the time that each horizontal division represents. To find the duration of a signal, multiply the number of horizontal divisions that the signal covers by the sweep time setting. For example, a pulse that takes up 2 horizontal divisions when the sweep time is set at 5 milliseconds per division is 10 milliseconds long. Based on these two settings, the oscilloscope produces a graph of voltage over time. If the level of the signal changes, the scope will display a varying trace that represents the changing value over time. If the signal level is stable, the scope will display a steady line representing that signal's voltage in relation to ground. There are several features of a signal that we can determine using the graph displayed on an oscilloscope. We can observe the waveform of a signal simply by looking at the graph. We may see a square wave, a DC level, or a pulse. We can also measure the voltage level or amplitude of the signal. If it is a DC level, set the input coupling switch to ground and use the vertical position control to set the reference point on the display. Return the input coupling switch to DC and count the number of divisions from the ground level to the trace. Multiply this number by the volts per division setting to find the input voltage. To find the amplitude of a varying signal, count the number of vertical divisions from the highest to the lowest position in the signal. Multiply this number by the voltage per division setting to obtain the peak-to-peak voltage. In addition to the amplitude of a signal, we may also measure its pulse width and period. To find the width of a pulse, count the number of horizontal divisions between the leading and trailing edges. Measure from the 50% level on each edge. Multiply the number of divisions that the pulse covers by the time-based setting to find the pulse width. The period of a signal is the amount of time it takes to complete a cycle. A cycle is one complete repetition of the signal. To find a signal's period, count the number of divisions that one cycle covers. Multiply this by the time-based setting. From the measured period, we can calculate a signal's frequency, which is the number of cycles per second it can complete. A signal's frequency is the inverse of its period. To find the inverse of a number, divide it into 1. For example, consider the frequency of this waveform. One cycle takes up 5 horizontal divisions when the time base is set for 50 nanoseconds per division. This indicates a period of 250 nanoseconds. This is the amount of time a complete cycle takes. From this, we want to determine its frequency, or how many times per second the signal occurs. So we divide 1, which represents 1 second, by 250 nanoseconds, or 250 billionths of a second. The result of this calculation is 4 million cycles per second, or 4 megahertz. To check this answer, multiply 250 nanoseconds by 4 million. You get an answer of 1, confirming that a signal with a period of 250 nanoseconds has a frequency of 4 megahertz. Measurements made on an oscilloscope are not extremely accurate. Your measurements are only as good as your interpretation of the screen, and the human eye is never 100% accurate. The principal advantages of an oscilloscope are the wide range of readings that you can make with it, and its ability to display a signal graphically. Now let's take a look at how the oscilloscope produces its graphic display. The oscilloscope uses a cathode ray tube as its display surface. This is a special purpose phosphor-coated vacuum tube, similar to the picture tube on a television. The face of the CRT glows when a beam of electrons strike it. A pair of electrostatic plates produces magnetic fields that move the beam around the face of the tube. The moving beam striking the phosphor produces the image that we see. The vertical section of the oscilloscope moves the beam up and down on the face of the screen to represent voltage, and the horizontal section of the scope moves the beam across the screen to represent time. Let's trace a signal through the scope to see how this happens. Many scopes have 2 voltage input channels that operate in an identical manner. The input channels of your scope, usually labeled A and B, or 1 and 2, are connected to the vertical driver, which moves the beam up and down. When you measure a signal with your scope, it first passes through the input probe. Many probes have a ×1 or ×10 switch on them. If the switch is set for ×1, the signal passes into the oscilloscope unchanged. If you select the ×10 setting, the signal passes through a high-impedance circuit consisting of a resistor and a variable capacitor. The purpose of using the ×10 setting is to increase the input impedance of the scope. The higher the impedance of the test equipment, the less it loads the circuit being measured. Loading the circuit means drawing a part of the circuit's current through the test equipment. In this illustration, the impedance of the scope and the circuit under test are the same, so the scope draws half of the current. This represents sufficient loading to reduce voltage readings and distort the signal. In extreme cases, loading may cause a circuit to cease functioning. ×10 probes increase the scope's impedance by a factor of 10. In this circuit, the oscilloscope draws only 1/10 of the circuit's current. Always be aware that using ×10 probes will attenuate the signal by a factor of 10. A 5-volt signal passed through a ×10 probe would display an amplitude of 0.5 volts. We call them ×10 probes because we must multiply the voltage displayed by 10 to get the signal's true amplitude. After the signal passes through the probe, it reaches the input coupling section of the scope. If we set the coupling switch for DC, the signal passes directly through. If we select AC coupling, a series capacitor added to the circuit strips the signal of any DC component. We can also set the input coupling switch to ground. In this position, the input to the vertical amplifier is grounded. This setting can be used to set the ground reference on the screen. The signal next reaches the vertical attenuation section. This consists of a voltage divider and the switch that you use to select volts per division. If you select the lowest voltage range on the scope, the signal will be applied directly to the vertical amplifier. If you select any other setting, the signal will be passed through a voltage divider, which reduces the portion of the signal applied to the vertical amplifier to a level that will not overdrive it. Selecting the wrong voltage setting can apply far too much voltage to the amplifier, which will result in incorrect readings and possible damage to the oscilloscope. Always check your vertical attenuation setting before taking any readings. The output of the vertical attenuator drives an amplifier. The vertical amplifier provides input to the vertical driver, which moves the electron beam up and down on the face of the screen. The variable volts per division adjustment on the vertical attenuator control will provide a variable change in the scale factor of the signal. This is handy when you want to compare several signals. Use the variable control to adjust the signal so that it fits right on a division line. Then look at the other signal. You will be able to quickly tell if they are the same. Moving the variable control from the locked position will cause the vertical attenuator to be uncalibrated. This can lead to an inaccurate measurement. When you are using your scope to measure amplitude, always ensure that the variable control is locked in the calibrated position. The vertical position control provides a variable DC bias to the amplifier. This bias alters the output to the driver and ultimately changes the position where the signal appears. Without horizontal motion, the vertical section would produce a straight vertical line representing the signal's voltage swing. In order to complete the display, we must add a time component to the voltage picture that the vertical section draws. The horizontal or sweep section provides this time reference for the display. A variable frequency oscillator produces a sawtooth wave that is conditioned and applied to the horizontal plates. This drives the beam across the screen at a regular pace, while the vertical section drives it up and down to represent voltage. To see a greater or smaller section of the waveform, we vary the speed of the sawtooth sweep signal by setting the time base or time per division switch. The higher the time base setting, the faster the sweep. Increasing the sweep speed will show a smaller portion of the input signal, and decreasing it will display more repetitions of the wave. A variable control on the time base selector can slow the speed of the sweep. You can use this feature to see an entire signal that does not all fit on the display otherwise. As with the variable vertical control, the variable time base control also allows for making quick signal comparisons. An unlocked variable time base control means that the time per division setting is invalid. Never check or adjust a signal's timing when the time base calibrate control is unlocked. With the sweep generator providing the time base and the vertical section the signal input, we now have a complete display. To make it easily readable, we must synchronize the two. Without synchronization, the time base generator may start a sweep when the input signal is at any point in its cycle. Under these conditions, the signal may be unreadable, like this. In order for the display to be stable, each sweep must start at the same point in the input waveform. The trigger circuit determines at which point sweeps will begin and controls the sweep generator. There are two main modes of triggering, auto and normal. With the auto or automatic mode, the scope will look for a trigger point. If it finds one, it will trigger. If within a specific period of time there does not occur a trigger point, the scope will trigger automatically. The auto mode will display a signal regardless of trigger. The trigger mode labeled norm or normal is the most versatile. This mode allows triggering over the widest range of trigger levels and is adjusted with the trigger level control. Unlike the auto mode, the normal mode will not display a signal without a trigger source. Now that we are in the normal mode, we must pick the signal that we wish to trigger on. We may use the signal on one of our input channels or on a third signal applied to the trigger input, which is used only for synchronization. Use the trigger source switch to select channel 1, channel 2, or an external sync source. The trigger circuit will enable the sweep generator on either the rising or falling edge of the signal used for sync. The trigger slope switch selects which edge to use. Once we have chosen the edge to trigger on, we use the trigger level to pick the exact point we wish to use. Now that we have chosen a sync point, the trigger circuit will produce an enable pulse every time that point occurs. If the sweep generator is not already executing a sweep, it will start one. If the trigger is properly set, the scope will produce a clear, stable display that does not drift. You can use this display to find amplitude, period, frequency, wave shape, and other features of a signal. If you do not understand any of the material covered so far, stop the tape and review Section 1 of this training package. In the last section of this tape, we covered the internal operation and basic controls of the oscilloscope. In this section, we will discuss its correct use. The oscilloscope is a complex and sensitive piece of equipment. Regular maintenance and proper care make it an extremely useful tool. Most oscilloscope manufacturers recommend that their scopes be calibrated once a year. A skilled oscilloscope technician should perform this alignment. Do not attempt this procedure in your shop. There are two adjustments that you can make to your oscilloscope. These are trace rotation and astigmatism. Trace rotation adjusts the beam for parallel placement on the graticule. To check it, set the input coupling to ground and the trigger to auto mode. Use the vertical position control to move the trace over the graticule's center line. Although the Earth's magnetic field will only slightly affect the scope's display, moving and bumping the scope can cause a rotation problem. It is important to check and adjust rotation to ensure accurate readings. To adjust the trace, locate the trace rotation potentiometer on your scope. This control is recessed to prevent accidental misalignment. Use a small screwdriver to line the trace up with the center line of the scope. The astigmatism control adjusts the beam for the clearest trace display. To adjust it, select the XY display mode and ground both input channels. Set both focus and intensity to mid-range. A small dot will appear in the center of the screen. Adjust the recessed astigmatism control until the point is as sharp and round as possible. Test probes provide signal information to the oscilloscope inputs. Attenuator or ×10 probes also require adjustment. You may calibrate these yourself. Attenuator probes reduce loading of the circuit under test by adding a large impedance to the input circuit. If this impedance is not matched to the scope's input impedance, the two will form either a peaking filter or a low-pass filter, which will cause problems when observing square waves or other signals with fast rise times. Rectangular waves are composed of an infinite number of sine wave harmonics. If some of these harmonics are blocked by the filter formed by the probe in the input section of the scope, the wave displayed will no longer be square. If there is too much capacitance in the probe circuit, square waves will show spikes like this one. If the probe circuit does not contain enough capacitance, square waves will be rounded. Another problem that a misaligned probe may cause is ringing, caused by unwanted resonance in the scope's input circuit. This is what ringing may look like. To prevent this type of inaccuracy, check your probes before each use. It is especially important to realign probes when they are moved from one channel or from one scope to another. Set the probe to the ×10 setting and connect it to the Probe Adjust tap on the front of your scope. Ground the probe to the scope's external ground tap. The calibration waveform displayed will normally have a frequency of 1 kHz and an amplitude of about 1 volt peak to peak. Set your scope to display several cycles of this waveform. Adjust the probe's trim cap so that the wave is perfectly square with no rounding, spiking, or ringing. Use a non-metallic alignment tool to prevent adding external capacitance that might affect the alignment. The capacitive effect of a tool increases with the amount of metal involved. Therefore, a metal-tipped plastic tool is acceptable, but a screwdriver is not. Now your scope and probes are properly calibrated and ready for use. Before actually measuring any signals, there are some oscilloscope characteristics that you must be aware of. One of the most important features of an oscilloscope is its bandwidth. This describes the highest frequency at which the scope can faithfully reproduce a sine wave. For instance, a 35 MHz scope can successfully draw a 35 MHz sine wave. However, it will not be able to reproduce a square wave of the same frequency without significant degradation. The reason for this is that square waves are composed of a large number of faster sine waves. As an example, a 35 MHz square wave has significant components of up to 175 MHz. Practically, this means that to display a square wave properly, the scope must have a bandwidth at least 5 times greater than the square wave's frequency. If you measure a signal outside the scope's bandwidth, the oscilloscope will still display it. However, do not attempt to align any signal that is outside of your scope's bandwidth. The error in the display will not permit enough accuracy to make any measurement correctly. Another feature of an oscilloscope is its trigger bandwidth. This specification is not usually printed on the scope, but is listed in its documentation. Trigger bandwidth refers to the scope's ability to capture quick pulses to use as a trigger. If a pulse is faster than the trigger bandwidth of the scope, it cannot be used as a trigger input. Keeping in mind these limitations, you are now ready to actually observe signals. The first step in checking any signal is to provide a proper ground point for the oscilloscope. Normally, you will connect your scope to a 3-prong grounded outlet and apply AC power to the unit under test through an isolation transformer. The probe's ground lead can then be attached to the chassis of the unit being tested. In this configuration, the oscilloscope provides a line ground to the unit under test. Without an isolation transformer, when the scope and computer are connected to outlets that are wired differently, line voltage may be applied to the ground lead. This will result in damage to the scope, the computer, and possibly the technician. Be sure to isolate either the scope or the unit under test when a possibility of conflicting grounds exists. This includes monitors, power supplies, and some network communication circuits. Once you have established a ground point, the next step is to choose the vertical settings for your scope. Use ×10 probes unless the amplitude of the signal you're measuring is so small as to make this impossible. Next, set the input coupling switch to ground and the trigger setting to auto. This will produce a flat line display at the reference level on the screen. Move the vertical position control to set an appropriate reference point on the graticule. Also, adjust the focus and intensity controls for a sharp line that is bright enough to read but no brighter. Focus will allow you to make a more accurate reading. Excessive brightness can cause small details of the signal to be lost, as well as burning the phosphor coating of the tube. Never leave your scope displaying an excessively bright signal for long periods of time. When observing digital signals, use the bottom of the screen. When measuring AC inputs, the center line is usually best. After setting your reference point, move the input coupling switch to either AC or DC. Use DC when tracing TTL or other logic signals. Use AC for differential outputs and for signals such as power supply and video output transistors, where the signal rides on a large DC level. If you are unsure of the type of signal you are going to observe, start with AC coupling. This will help prevent overdriving the scope, and the signal will tend to settle onto the screen. Next, set your vertical attenuation or volts per division switch. Remember that if you are using ×10 probes, the amplitude of the signal on your scope's input will be 1/10 of its original value. For example, a 3 1/2 volt signal has an amplitude of 0.35 volts after passing through an attenuator probe. On some scopes, there is a second pointer on the volts per division switch to use with ×10 probes. On other units, you must calculate the setting yourself. If you do not know what the amplitude of the signal will be, always start with the highest range and work down. This avoids overdriving the vertical amplifier and also prevents mistaking noise for the signal in question. Now that your vertical controls are set correctly, set the time base or time per division switch appropriately. If you know the frequency of the signal to be observed, use it to compute the period and pick an appropriate setting. For instance, suppose that we are checking a signal with a stated frequency of 4 MHz. Using the equation period equals 1 over frequency, we find that one cycle of the wave takes 250 nanoseconds. It is usually best to display 1 or 2 complete cycles of the signal. 2 repetitions of this signal would take 500 nanoseconds. Since there are 10 horizontal divisions on our scope, a setting of 50 nanoseconds per division allows us to see 2 cycles of the wave. If your scope does not have a fast enough sweep time for the signal you want to measure, use the time-based magnification control. This option allows you to stretch out a portion of the signal, usually by a factor of 5 or 10. For instance, if the fastest sweep time on your scope is 100 nanoseconds and you have a 5 times magnifier, you can magnify the signal to a range of 100 divided by 5 or 20 nanoseconds per division. Remember that when using the magnifier, the time-based representation is not nearly as accurate. The magnification is also useful when you want to observe details in a signal that occur very close together but don't want to change the time base. If you do not know the period of a signal, start with a slow time base and work your way up. If the time base is set too slow, the signal may appear blurred. If the time base is too fast, the signal may appear to be a DC line, which can mislead you into believing that no signal is present. Now that your amplitude and time base settings are correct, you are ready to connect the probe to the signal you wish to observe. If you're using the simple pointed tip, make sure that the ground ring does not contact any of the circuitry and short it out. If you are using a hooked probe tip, make sure that it is securely attached to the body of the probe. In either case, make a firm connection between the probe and the point being measured. Do not touch the probe tip or the test point with your fingers. This can add stray capacitance to the circuit and distort the reading. If you have selected Auto Trigger, you will now see a display of some type. If either the volts or time per division requires correction, fix them now. The final step in observing a signal is to produce a stable picture by synchronizing the sweep with the signal being displayed. In this case, we are observing only one signal, so the process is not complex. Select Internal Trigger and the channel being used, in this case channel 1. Now, select Normal Trigger and adjust the trigger level potentiometer until the display stabilizes. Now that you have a clear display, let's see what differences some triggering options can make. First, change the trigger slope from positive to negative. Notice that the display now begins with the falling rather than the rising edge of the signal. Next, move the trigger level potentiometer. The point on the edge at which the signal begins varies as you move this control. It can be so badly misadjusted that it will not trigger at all. Next, let's look at the effect of variable hold-off. Variable hold-off controls the minimum amount of time that must elapse between one sweep and the next. We do not often need to vary this setting, but it can stabilize the display of certain signals. We have now covered all the steps necessary to observe simple signals. First, calibrate your probes and find a proper ground connection for the scope. Then set up your coupling, vertical attenuation, and time base. Connect your probe and select Auto Trigger mode. Once you have confirmed that the signal is present, select the trigger slope and adjust the level for the clearest display. Now, let's look at some slightly more involved uses of an oscilloscope. First, we will use the dual display function to observe and compare two signals. The oscilloscopes that we have use at least two input channels and associated vertical sections. The two are almost identical and each is capable of displaying a signal on the screen. This dual trace capability presents us with several additional settings to select. We may display either channel 1 or 2 alone, or we may combine the two in one of several manners. We can view both channels at the same time by selecting the dual option on the display panel. On some scopes, there are settings labeled chopped and alternate. This refers to two possible methods of displaying both signals at once. Since the oscilloscope has only one electron gun, it cannot draw both signals at the same time. In the alternate mode, first one trace is drawn completely and then the other. In the chopped mode, the beam draws a portion of one, then a portion of the other, usually alternating at a frequency of 250 kHz. The chopped mode is best for slow signals on time bases of 1 millisecond or slower. At these rates, if the signals were drawn alternately, the first would fade from the display before the second was drawn. The alternate mode is suitable for faster signals. Chopped mode does not work well with these signals because the motion between one signal and the other becomes visible at higher speeds. In addition to displaying the two signals separately, we can combine them using the Add Display setting. This option displays the sum of the two inputs at any given time. If we add two identical signals, the display will show a wave with double the amplitude of either. Many scopes have an invert option on the second channel input. This allows us to amplify the difference in two signals. If we add two signals that are exactly opposite, a flat line will result. When displaying two channels at once, we must also decide which channel to use as our sync source. If the two signals have different frequencies, always sync on the slower one to produce the clearest possible display. If we use the faster signal for sync, sweeps will begin at widely varying points on the slower signal, and there will be no possibility of a stable display. If the slower signal provides the sync, there may be some instability in the faster signal, but the display will be much clearer. A complication arises when the two signals are not related. Some scopes provide a vertical trigger mode when internal trigger is selected. This means that the vertical mode switch determines the trigger source. If the vertical mode switch is set to channel 1, then the trigger source is channel 1. If the vertical mode switch is set to channel 2, then channel 2 will be the trigger source. The magic comes about when the mode switch is set to alternate. This will cause the scope to trigger on whichever trace is being displayed at a given time. By using the vertical trigger mode, two unrelated signals may be displayed correctly. If the vertical mode is set to add, then the combination of the two signals becomes the trigger source. And if your scope is in the chop vertical mode, the vertical trigger will keep your scope from triggering on the chop frequency instead of the signals you are trying to look at. Before ending our discussion of setting up oscilloscopes, we must cover the use of an external trigger source. This allows us to observe one or more signals in relationship to the timing of a third. To set up external sync, connect a probe to the jack-marked sync source on the front of the scope. Then select the external option on the sync source control. Always use the ×1 setting on the probe used for sync unless the input has an amplitude of 20 volts or more. Since the trigger circuitry detects changes in signal level, the greater the range that we give it, the more easily synchronization can occur. The trigger input on a scope has a coupling control similar to that on the display channels. In addition to AC and DC settings, it may have high and low frequency reject positions. The low frequency reject mode will attenuate trigger signals which are below 10 kHz. This can be useful in reducing low frequency trigger interference such as 60 Hz hum. The high frequency reject mode will attenuate trigger signals above 100 kHz. This mode can be used to reduce high frequency noise from the trigger source. A good example of the use of external sync is floppy disk drive alignments. In these procedures, we observe the outputs of the drive's read amplifiers in relation to the index timing signal, which occurs once every revolution of the diskette. Some scopes also have a single trigger mode option. This setting causes the scope to sweep just once when a pulse appears on the trigger input. Now that we are familiar with the basic operation and reading of an oscilloscope, let's look at some common signals. The first signal that we will observe is an address line. A data line will look very similar. This is a TTL level signal, so we set our vertical attenuator to 0.1 volts per division and our probes to ×10. With these settings, each vertical division represents 1 volt. We will set our time base to 1 microsecond, but since there is no repetitive frequency to this signal, the time base is not critical. As you can see, the output of an address or data line does not produce a clear, stable display. This is because the voltages on these lines do not have a set frequency or period. In order to determine that the line is working, we merely observe that it can produce valid TTL highs and lows. We don't know that the data being produced is the correct data, only that it has valid levels. Next, let's look at a clock signal. This signal has an amplitude of about 5 volts, so the vertical attenuation settings remain the same. The frequency of this clock is supposed to be 4.77 MHz. To calculate its period, we take the inverse of that value, or divide it into 1. This indicates a period of about 210 nanoseconds. To display 2 cycles of the waveform, we will select a time base of 50 nanoseconds per division. Notice that this signal appears to be low for a longer period than it is high, or that the ratio of high and low times is not 50-50. This characteristic is expressed as a duty cycle. To obtain the duty cycle of a signal, divide its high time by its period. In this case, the signal is high for 70 nanoseconds each cycle, and its period is 210 nanoseconds. Dividing 70 by 210, we arrive at a duty cycle of 33% for this signal. Another feature of a signal that we may need to observe with our scope is pulse width. A pulse may be either low-going or high-going, depending on the signal's active state. If the signal is active high, we will measure its high time, and if it is active low, its low time. Trigger slope is critical when observing pulse width. Notice the difference in the display of this active high pulse as we change the trigger slope from positive to negative. When measuring or adjusting pulse width, we usually count from the 50% mark on the rising and falling edges of the signal. To obtain the most accurate measurement, reduce the time base until the pulse fills most of the screen. In this example, the pulse covers 5 divisions when the 50 nanosecond setting is used. This gives a pulse width of 250 nanoseconds. These are some of the most common types of measurements that you will make with your scope. There are many other signals that you may observe, but the same basic rules apply. Use the ground coupling and auto trigger to find your reference point before beginning. Set vertical attenuation and time base to the appropriate ranges. Start with a high voltage and slow time base if you're not sure. Use the correct trigger slope when measuring pulse widths. When observing two signals at once, sync on the slower signal. When using dual display, use the chop mode for sweep rates slower than 1 millisecond. For higher frequency signals, use the alternate mode. These rules will help you use your scope easily and efficiently. Now stop the tape and complete Section 2 in the workbook. In the previous section of this tape, we discussed the operation and use of the oscilloscope. Now, let's look at some other types of test equipment. This is a frequency counter. Its purpose is to time pulses or waves and report the results in one of several units. Frequency counters are used when a period or frequency must be measured more precisely than an oscilloscope will allow. These units measure and calculate duration internally and present the results on a digital display. This eliminates errors of interpretation that are always present in oscilloscope readings. Like an oscilloscope, this frequency counter has two input channels labeled A and B. However, there is no external trigger jack since the input signal always provides the trigger pulse on these units. The probes used on this counter are interchangeable with those used on 1 megaohm input oscilloscopes. The frequency counter's input channels each have input controls. The positive-negative slope button selects which edge of the input signal to trigger on. Channel A also has a trigger level adjustment. As on an oscilloscope, this controls the point on the signal edge at which the unit triggers. On this counter, pull the knob out to enable variable trigger. A times 10 switch attenuates the incoming signal by a factor of 10, just like the times 10 switch on a probe. If the times 10 settings on both the counter and the probe are selected, the signal is attenuated by a factor of 100. The Lpf switch adds a low-pass filter to the input circuit. Select this option when measuring signals of 5 kHz or less to prevent false triggering on high-frequency noise. In addition to the input channel switches, there are a number of display control settings. The reset button causes the counter to restart at 0 and the display to clear. The test button produces a string of 8s on the display to assure that it is functioning. The Kmu/mm switch selects whether the results are displayed in kilohertz and microseconds or megahertz and milliseconds. The next set of buttons control the type of measurement that the frequency counter will take. The frequency A selection computes the frequency of the signal on channel A. On most inexpensive counters, the results of a frequency reading are only accurate on sine waves. To determine the frequency of a wave or pulse train with fast rise times, use the period setting and convert the results to frequency. The period A switch selects this function. For example, to measure a hard drive motor's rotational speed, we check the period of its index pulse. In this case, the result is 16.662 milliseconds. To convert this to frequency, divide 1 by the period. This indicates a frequency of 60.16 Hz. The counter also has settings for ratio, interval, and total. Ratio divides the frequency on channel A by that on channel B and provides the results. Interval displays the time elapsed between the pulse on channel A and that on channel B. Total counts and displays the total number of pulses that occur on channel A. The final set of controls sets the resolution of the display, or where the decimal point appears. This only affects the number of places displayed, not the accuracy or range of the counter. Now that you are familiar with the frequency counter's controls, let's watch its correct use. As an example, let's measure the motor speed on a 5 1/4 inch floppy drive. Set the probe to the times 1 setting, since the signal to be measured has an amplitude of less than 20 volts. Next, find an appropriate ground point. To find motor speed, observe the index pulse coming from the drive. Since this pulse has a fast rise time, use the period A setting to measure its period. Next, select the trigger slope. Since the index pulse is low going, use negative trigger. This drive speed is specified at 300 RPM, which converts to a frequency of 5 Hz. Engage the low-pass filter switch to eliminate the possibility of triggering on high-frequency noise. If we convert 5 Hz to period, we arrive at a figure of 200 milliseconds. To measure this accurately, set the Kmu/mm switch to measure period in milliseconds and set the resolution switch to 0.1 microseconds. Adjust the trigger level until the display stabilizes. Check the reading by converting the displayed period to frequency. Now that we know how to operate a frequency counter properly, let's look at some common operational mistakes. A very common error is to attempt to read the frequency of a square pulse directly. Most inexpensive counters are not designed to do this. As you can see, the results are somewhat inaccurate. Another common mistake is to set both the probe and the counter to the ×10 mode. This attenuates the signal by a factor of 100, which makes triggering impossible if the input amplitude is low. Finally, using the low-pass filter option on signals faster than 5 kHz will result in incorrect readings. Before leaving the subject of frequency counters, let's look at another use to which we can put them. We can use a frequency counter to check the AC line frequency if necessary. Since this is a very high AC voltage, we will set the counter up somewhat differently. In this situation, set both the probe and the counter switch to ×10. This 100-fold attenuation is necessary to prevent damage to the counter. Do not ground the counter when measuring the AC line. It would be possible to use unmatched ground points and destroy the meter. Place the probe tip carefully into one of the slots in the AC plug. The AC line will contain a sine wave of about 60 Hz. Set the counter to read period and engage the low-pass filter. The reading should be about 16.66 milliseconds. These examples illustrate the basic use of a frequency counter. There are a few simple rules to keep in mind. Use the period setting when measuring rectangular waves. The frequency function is not accurate on digital signals. Always engage the low-pass filter on signals slower than 5 kHz, but never on signals that are faster. Do not engage the ×10 switches on either the counter or the probe unless the signal amplitude is greater than 20 volts. Do not engage them both unless the signal's amplitude is greater than 100 volts. With both ×10 options selected, the counter can accept voltages of up to 2000 volts. However, the probes are generally rated to carry between 500 and 1000 volts. These simple precautions will make using the frequency counter a simple and productive task. The next type of test equipment that we will cover is the volt-ohm meter combination, commonly called a multimeter. There are two distinct types of multimeter, digital and analog. The digital meter displays readings on an LCD or LED screen, while the analog meter uses a magnetic movement and scale. One advantage that a digital meter has over a passive analog device is its high stable input impedance, usually 10 megohms or greater. This high impedance decreases loading of the circuit under test, which makes the digital meter especially useful for measuring high impedance circuits, like this monitor. The analog meter, on the other hand, has a variable input impedance expressed in ohms per volt. To determine the input impedance of an analog meter, multiply the ohms per volt rating by the full-scale value of the range selected. For instance, a meter rated at 10 kiloohms per volt has a resistance of 20 kiloohms on the 2-volt scale and 200 kiloohms on the 20-volt scale. In other words, the meter's input impedance decreases as the voltage scale is reduced, so the meter loads more on lower scales. Notice that the analog meter reads a lower voltage at this point than the digital meter did. The way to offset this disadvantage is to use a meter with a high ohms per volt rating, or to use an active component meter like a vacuum tube voltmeter or an FET meter. When measuring steady voltages, the DVM is also more accurate and easier to read than an analog device. There are two reasons for this. The first is that analog meter readings are subject to errors of parallax. This means that your reading appears to vary as you view the meter from different angles. The DVM presents readings on a numeric display, so this type of error does not occur. The digital voltmeter can also display much smaller current changes than an analog meter can. These two factors make its readings extremely accurate. A final advantage that the digital meter has over an analog device is the ability to deal with reversed polarity. When negative voltage is applied to an analog meter, the movement jerks violently backwards and may be damaged. A digital meter would simply display the voltage as negative. The digital meter, however, has a few disadvantages. One is that it requires an external power source to make readings of any type, while the analog meter needs a power source only for resistance measurements. The other disadvantage to a DVM is that it is not well suited for checking capacitors. It cannot check diodes or transistors either unless it has a diode check scale. In many digital meters, the resistance setting doesn't generate enough voltage to forward bias a diode. Also, the digital scale doesn't reflect varying voltage as well. An analog meter, however, performs these functions easily. To check a capacitor, set the meter to read resistance on the lowest scale. When you place the meter leads on the capacitor, the pointer will jump if the capacitor is operating correctly. The size of the jump is related to the capacitor's value. To check a diode, select the resistance function and the times 100 scale. The diode should read mid-range in one direction and open when the leads are reversed. To check a transistor, simply treat it as a pair of diodes. Measure from the base to collector and then reverse the leads. A good junction will read mid-range in one direction and open in the other. Repeat this process for the base emitter junction. As a final check, measure the resistance from emitter to collector. The resistance must be at least 1 megaohm and may be much higher. These are some of the lesser-known features and quirks of multimeters. Now let's discuss some of their more common uses. When measuring voltage, use a digital meter for greatest accuracy. Always be sure to select the correct function when using your multimeter. If you select an AC scale to read a DC voltage, for instance, you will get incorrect readings. Take special care never to select the resistance function when you want to measure voltage or current. This setting will introduce additional current into the meter and the circuit under test, which will alter readings and may damage the meter or circuit. Also, remember that you provide ground reference to the meter through your negative lead. The reading displayed represents the difference in potential between the black and red leads. For example, if you were going to measure a 12-volt supply and place the negative lead on the 5-volt line by mistake, the meter would read 7 volts, the difference between the two. Finally, as with all test equipment, if you do not know the value of the signal to be measured, start with the highest range and work down. This will prevent incorrect readings and possible damage. There is one voltage measurement that we do not perform with a voltmeter. When checking the anode voltage on a CRT, we use a high-voltage probe. This device is designed to measure the 10 to 40 kilovolts on a tube's anode. To reduce the possibility of shock due to accidental contact, remove watches and jewelry. Do not wear a static bracelet since it provides a current path to ground. Secure the probe's ground lead to a good chassis ground point. Insert the tip of the probe under the cap on the anode lead. For safety, use only one hand. Read the voltage off the kilovolt scale on the body of the probe. A high-voltage probe has only one purpose, that is, measuring the anode voltage of a CRT. Do not attempt to use it to discharge a tube. The final piece of test equipment that we will mention is the variac, or variable transformer. The name is somewhat misleading because most of these units are not transformers at all. They do not isolate the unit they are connected to from line ground and must not be used in place of an isolation transformer. The purpose of a variac is to control the AC voltage provided to the unit under test. This is especially useful when troubleshooting power supplies or monitors that are going into overvoltage modes. Use the dial on the variac to set the voltage to a level that allows the unit to operate without shutting down. This will allow you to use other test equipment to isolate the failure. This completes the test equipment usage section of this videotape. Stop the tape and complete the third section of your workbook. In the final section of this tape, we will discuss another computer repair tool, diagnostic programs. We will not attempt to explain the use of specific programs, but rather try to give an overall picture of their purpose and use. For specific operational instructions, refer to your diagnostic manuals. Diagnostics serve two basic purposes. They help detect failures and also allow us to exercise system functions. For our purposes, we will divide diagnostics into four basic types: memory tests, media verification, peripheral diagnostics, and alignment programs. Alignment programs are not diagnostic in the strictest sense of the word. They do not tell you whether or not a unit is failing. Instead, they exercise the system in ways that allow you to check and, if necessary, correct certain alignments that are required for proper system operation. Use these programs during routine maintenance or when a unit is failing. Memory diagnostics of some type are available for most Tandy computers. The basic purpose of these programs is to write a specific byte of data into RAM, read it back, and verify that the data returned is the same as the data written. There are several varieties of RAM test, each of which exercises the memory in a different way. There is no single test that checks for all possible RAM failures. The time involved would be prohibitive. As an example, if you removed a brand new 16K machine from its box and immediately started a RAM test that tested all locations with all data patterns in all possible combinations, the unit's warranty would expire long before the test finished. For this reason, RAM tests are designed to check for certain types of common failures. They may or may not detect failures of other types. The Checkerboard Ram Test writes alternating patterns throughout the memory, one pattern in the first location, a second pattern in the next, and then back to the first, and so on. This test will detect a hard failure rather quickly, but is not very good at finding RAM chips that fail only when certain patterns are written to them. The Modified Address Test uses a different type of algorithm. It writes a unique pattern based on the address to each location. This reduces the possibility of recovering the correct data from a bad RAM, which can happen with checkerboard-type tests. Modified address tests also check the RAM for pattern sensitivity, which is inability to hold certain combinations of bits. Rotating bit tests check the RAM's ability to contain a single odd bit. In some cases, a RAM functions if the zeros and ones stored in it are evenly mixed, but breaks down when asked to store a single zero among a large number of ones, or vice versa. These are the most common types of memory tests. Specific machines may also have others. Since each type of memory test is best at finding a certain type of failure, you must run all of them to check the unit thoroughly. Even so, the customer's applications packages may stress the memory in a different way. Even the best diagnostics are not infallible. The next class of diagnostics that we will discuss are media verification diagnostics. These check the storage capabilities of hard, floppy, and other types of drives. With these diagnostics, good, freshly formatted media are extremely important. When testing floppy drives, bulk erase and format the test diskette. For cartridge drive tests, format the test media, but do not bulk erase it. Bulk erasing a cartridge destroys irreplaceable factory-written information. Formatting does not affect this special data. When testing non-removable media, always format a new disk or one that has been aligned before testing. Otherwise, the errors reported may be related to a damaged format rather than a damaged drive. Remember that formatting a hard disk destroys any data stored on it. Many disk reliability tests have an option to disable retries. If the unit under test supports this feature, use it. With retries enabled, the drive controller board will attempt to read or write up to 16 times before reporting an error to the diagnostic. This means that a marginal drive can easily pass all tests when retries are enabled, but will fail quickly when the controller must report all errors that it encounters. There are several test options on disk verification diagnostics. The Write, Read, Verify test ensures that data can be written to the media. However, it does not test the media's ability to retain the data. For this, you must select one of the read-only options and let it run for several passes. Read tests usually include test all tracks sequentially and test random tracks. Be sure to run both of these options. Most drives seek differently when they are moving to an adjacent track than when they must go halfway across the disk. Using both tests increases your chances of detecting failures in either mode. The last class of programs are those that we call peripheral diagnostics. This covers a wide range of tests, including auxiliary processors, serial and parallel I/O channels, and external devices such as printers and modems. Before assuming that a unit is working, test all peripheral functions. If a unit that came into your shop for a memory failure also has a serial I/O problem that you do not fix, you may have to repair it later, and you certainly won't have pleased the customer. Many peripheral tests use some type of loopback connectors. Make sure that these are in good shape, or you may waste time trying to fix a computer when it was actually your equipment that failed. Also, some mandatory modifications may cause a peripheral diagnostic test to fail. If you suspect this, check your technical bulletins for confirmation. The information in this section is intended to stress the importance of using diagnostics properly, as well as some limitations of these diagnostic programs. It is to your advantage to test a unit in every possible way before releasing it to the customer. This means that you must run all diagnostics for more than 1 or 2 passes. Intermittent problems, which are the cause of most customer dissatisfaction, will often not show up on the first test. Be sure to duplicate the function that the customer attempted before assuming that the problem is fixed. To maintain a high level of service, utilize all of your tools, including diagnostic test software, on every unit you repair. This completes the Tandy Radio Shack test equipment and diagnostic software training tape. Stop the tape now and complete the last section in your workbook.